Alright everybody, welcome back. In this video we're going to look at examples related to the direct comparison test and finding out if integrals converge or diverge by using direct comparison. And really the primary gist of direct comparison is this. If we can find an integral that is larger than the one that we're looking to determine its convergence or divergence, if we can find one that's larger on the entire interval of integration that converges, then that shows that the one that we're looking at converges. Similarly, if we can find one that's always smaller on the interval of integration that diverges, we can show that the one that we're comparing to diverges. So we're looking for either a bigger convergent integral to show that this converges, or a smaller divergent integral to figure out if this converges or diverges. It doesn't do any good to find either of the other two cases. When we find a bigger integral that diverges, that doesn't help us, and if we find a smaller integral that converges, that doesn't help us. So one of the things that we're going to do in trying to determine what integral to use to compare this to is kind of play our hunches. Do we think that the original integral converges or diverges? And that's where we're going to start here with example 2. Do we think that the integral from 3 to infinity of 1 over x plus e to the x dx converges or diverges? And you think about this a little bit. My personal hunch right now is I think that this integral converges. So I'm going to try and find an integral that is always larger than this one, an integrand that's always larger than the integrand of this integral on the interval from 3 to infinity, and then try and show that that one converges. And I know, based on the way that fractions work, that 1 over x plus e to the x is going to be less than or equal to 1 over e to the x for x values greater than or equal to 3. How do I know that? Well, because the denominator of this fraction is going to be larger than that for all those values of x, and therefore the other fraction is going to be larger. So now the question is, can I show that the integral from 3 to infinity of 1 over e to the x dx converges? Since it's always bigger, if I can show that it converges, then that proves the convergence of my original integral. If I, however, show that it diverges, that tells me nothing, and I have to look and start again and look for another function, or kind of change my perception of whether I think this converges or diverges. But in this one, I've chosen wisely. This is equal to the integral from 3 to infinity of e to the negative x dx, which is the limit as b goes to infinity of the integral from 3 to infinity of e to the negative x dx. And the value of that is, the antiderivative of that is just negative e to the negative x. I'll change that up a little to b. I do that sometimes to get to e like that. And so this is the limit as b goes to infinity of negative e to the negative b minus negative e to the negative 3. And as b goes to infinity, this exponent goes to negative infinity, and therefore this term approaches 0, and so this limit is e to the negative 3. So that converges. And now I'm going to write a concluding statement here. Since 1 over e to the x is greater than or equal to 1 over x plus e to the x, for x greater than or equal to 3, and the integral from 3 to infinity of 1 over e to the x dx converges, then the integral from 3 to infinity of 1 over x plus d dx converges by direct comparison. Okay. All right, let's look at example 3 using direct comparison. Determine if the following integral is convergent or divergent. The integral from 3 to infinity of 1 over x minus e to the negative x dx. My personal hunch is that this one's going to diverge, but I'm not really sure. My initial thought for comparison, as x goes to infinity, e to the negative x goes to 0, so I want to compare this to 1 over x, since the other term goes to 0. And what's true about this case is, since as x goes to infinity, we're subtracting something away, this one is, the denominator of the original is slightly smaller than the denominator of 1 over x. And so this is going to be greater than or equal to 1 over x, for x greater than or equal to 3. Alright, so we have it slightly bigger than this function. The integral from 3 to infinity of 1 over x dx diverges because it is a p integral. This is one of those that we talked about being incredibly important a few videos ago. This diverges. This is a p integral with p equal to 1. So this diverges. And so our original here is bigger than a divergent integral. That means that it's going to diverge. So, since 1 over x minus e to the negative x is bigger than 1 over x, for x greater than or equal to 3, and the integral from 3 to infinity of 1 over x diverges, the integral from 3 to infinity of 1 over x minus e to the negative x dx diverges by direct comparison. All right, last one here. The integral from 1 to infinity of 1 plus 3 sine to the 4th of 2x over the square root of x dx. Okay, what can we compare this to? Well, what we compare it to kind of depends on our initial hunch. And our initial hunch is, well, my initial hunch is that this one diverges, I think. So I want to find a function that diverges that is always smaller than this one. Okay? And since sine to the 4th always has to be greater than or equal to 0, this function is always greater than or equal to 1 over the square root of x. And then I'm again going to use my conception of the p integral. This is 1 over the square root of x dx. And this is equal to the integral from 1 to infinity of 1 over x to the 1/2 dx. This diverges because it is a p integral with p less than 1. So, since 1 plus 3 sine to the 4th of 2x over the square root of x is greater than or equal to 1 over the square root of x, for x greater than or equal to 1, and integral from 1 to infinity of 1 over square root of x dx diverges. That means that our original integral here, drop a 3, diverges by direct comparison test. Alright, so one of the toughest things for you is going to be to determine whether you think the original function converges or diverges, and what an appropriate function to compare it to will be in that case. And you're going to make mistakes. Sometimes you'll think that it converges, and you'll pick a function that it is always smaller than, and unfortunately you'll find that that function diverges, and it will be inconclusive for you, and you'll have to pick again. And it takes a little bit of perseverance when you're first getting used to these, but as you do more and more practice with them, you should get better at determining what would be a good function to compare to, and you're trusting your gut about whether the original function converges or diverges. Alright, that's the end of this video. See you guys next time. Have a great rest of your day.